Okay, we're going to continue on here. Not surprisingly, still chapter 14 here. Last time we talked about something. I believe we talked about weak acids and again, Ka problems and also weak bases, which are Kb type problems. Remember that because they are weak acids or weak bases, they're pretty much an equilibrium type of situation, which does mean that you do need to do an ice table for these guys. In the case of the weak acid, you basically do your ice table. You would solve for X, and X would equal the H plus concentration, which means you could get the pH. If you are doing a weak base problem, you also will still do an ice table. You will still solve for X. The difference here, though, is because it is a base, X will equal the hydroxide concentration, which means you typically got to go POH first and then to the pH. So they're very similar in terms of the way we calculate it. And as we talked about, you can calculate them just like any other equilibrium. You can, if you have a perfect square situation, do that. You could do the assumption. You could solve it with the quadratic, so all pretty much the same way. Again, we just kind of go into the pH equation or the POH equation, depending on which one you have. Remember that we also talked about the relationship between Ka and Kb, which means if you take Ka times Kb, it equals Kw, which basically means it equals water. And very often people, when they are doing calculations, will sometimes come across situations where they perhaps don't do the calculation correctly because, we talked about it as well, not being able to write the equation correctly. So again, that's really important to make sure that you understand how these equations are written and that you're able to write them correctly. And to determine whether or not you should be using a Ka or a Kb sort of value in a situation, it really is dependent on what you see on the product side. And if you see on the product side, really H plus or H3O plus over here, it definitely should be a Ka value that you're using there in your ice table. If you write the equation and you see hydroxide over here on the product side, that's a basic type situation, and you really should be using a Kb. So again, those things do go together, and you want to make sure that you're able to do that because if you don't write the equations correctly, you will be doing perhaps an acid calculation when you should be doing a base calculation and vice versa. So again, it's really important. And this is a way that we can kind of go from one value to the other. And that Kw is still the same value of 1 times 10 to the minus 14. So you can use that to convert it. So maybe you are given a Ka value in a problem, but you really need the Kb, which is very common in terms of the problems we're going to talk about here in just a second. And vice versa. Maybe you have the Kb and you need the value so you can switch it. We also talked about, I think, percent hydrolysis, percent ionization. And percent ionization is the concentration of the free H plus divided by the concentration of the initial acid times 100%. As we talked about, the percent ionization is sort of dependent as well on the concentration of the acid that you have. So if you have a really large concentration, the percent ionization will be a lot lower because you're only losing a little bit of a larger amount. If the concentration you're starting with in terms of the acid is relatively small, whatever you do lose is going to be relatively significant and you'll have a greater percent ionization. This is also essentially how we check our assumption. When we make our assumption that X is equal to 0, this is essentially how you check it. And the idea here, if it's less than 5% ionized, then it's okay. If it's greater than 5% ionized, there's going to be kind of significantly amount of change that's occurring and you can't really use it. We finished up, I think, talking about acid strength and a little bit of some things that you look at. In a acid with no oxygen, we look at bond enthalpy or energy. And bond enthalpy, most of our guys with no oxygen, this comes from group 7. And acid strength actually increases as you go down group 7. So like HF would be technically up here, HI would be down here, and it gets stronger of an acid as you go down. The reason for that is the bond energy gets smaller as you go down. So because the bond energy gets smaller as you go down, it makes it easier for that H to come off, which means it's going to be a much stronger acid than say something like HF, which has a really large bond energy, which means it's going to hang on to its hydrogen a lot longer, a lot stronger than say HI. So it's not going to release as much hydrogen into the solution and will make it a lot weaker of an acid. When we do have oxygen kind of involved with our acids, we look at one thing, either the oxidation number, our state, or the electronegativity. And the idea, usually when you have acid with oxygen, you oftentimes will have this bond associated with it. And this is, again, a polar bond to begin with. And really, this is the hydrogen that's going to get popped off there to be making an acid. And in this sense, what we would look at is we would look at the electronegativity values of the central atom if it is the same oxidation number. So I think we looked at maybe like chlorine and bromine in an example. And in those acids, they had the same oxidation state. So we then would look at electronegativity values. We also looked at a bunch of acids that had chlorine as the central atom. And again, they all would have the same electronegativity. So then you would look at the oxidation number or state of each of those things. Any questions on any of that stuff there? Yeah. So I think this is where we lay it up, I think. So let's talk a little bit about salts and properties of salts. And let's first talk about really the idea of sort of where salts come from. So when we have a reaction of an acid and a base, typically there's two things that we make, and that is a salt and water in most cases. And a salt really is an ionic compound. And it's really derived from what is left over after the acid gives away its H plus, and a lot of times the base gives away its OH minus. It's the other ions coming together here that will make the salts, the positive guy and the negative guy essentially coming together. So for example, if we had HCl, bless you, plus some sodium hydroxide, these guys are going to switch partners. We will get some sodium chloride and some water being made. And obviously here, this would be our salt, which is basically the sodium ion and the chloride ion coming together from the acid and base in this particular case. So when we look at salts, it's really important sometimes to think about where the salt comes from and sort of our relationships that we talked about in terms of, if it comes from something that's weak or strong and how that will affect its reaction. But what we're going to really talk about here, sort of in this, is the idea that when we do have salts, they can, in certain cases, continue to react with the water that is there. So they can continue to sort of react with the water. And in some cases, the result of this is the salt plus the water here will react in a way where perhaps maybe the water will send that over there and it will produce some hydroxide. The salt could also react with the water where perhaps the salt will send the H plus over and it will produce H3O plus. So the effect of these reactions where we produce these salts and they're obviously in the presence of water and they can continue to react can obviously affect the pH of the solution, since in this case we're producing more hydroxide. In this case, we're producing more H3O plus or H plus, and that's going to have an effect on the pH of the solution. Now, what kind of determines whether or not this reaction will happen is what is sometimes referred to, or actually what this reaction is sometimes referred to as a hydrolysis reaction, which means basically is we're going to have a salt and water continue to react and again affect the pH of the solution. Questions on that there? So let's take a look at some different types of salts and talk about sort of where they come from and the effect that they will have on the actual solution. So let's start with neutral salts. So neutral salts are salts that contain an alkali metal are an alkaline earth metal, except for beryllium. And that is group 1, right? And that is group 2 on the periodic table. And if you remember from our conversations, essentially, most things in group 1 and group 2 are pretty much where you get your strong bases from. So those are where a lot of the strong bases that have hydroxide come from, things like sodium hydroxide, potassium hydroxide, calcium, strontium, barium hydroxide. That's where a lot of these strong bases actually come from. So if you remember, we talked about the relationship of sort of our acid and conjugate base, or base and conjugate acid. So just a reminder on that relationship is if we have a strong acid, is conjugate base will be relatively weak. And if we have a strong base, is conjugate acid will also be relatively weak. Now, if we have a weak acid, its partner, its conjugate base will be relatively strong. And if you have a weak base, its conjugate acid will also be relatively strong. So this type of relationship is really important in terms of whether or not you would predict any type of hydrolysis reaction occurring. So if we took a salt like sodium chloride, which is basically sodium ion and chloride ion, as I just wrote in the previous example there on the last slide, that probably came from the combination of two things. It probably came from the combination of hydrochloric acid, which is a strong acid, along with the reaction of sodium hydroxide, which is a strong base. So what we have left over here is basically two parts of this salt that they both really come from a strong acid and strong base, which means they would fall over here in this category, and they will be relatively weak, which means they will not continue to react with water. They're what are considered a neutral salt. They're just going to kind of hang out there, float around. They're not going to go find water and do any type of reaction with it. And we would expect the pH of these guys basically to be 7. So if you have some type of salt that basically originated from a strong acid and a strong base, you basically will know that the pH of that salt solution should be neutral, and it should be a pH of 7 in that particular case. Any questions on that there? So let's talk a little bit about, say, some salts that are basic. So for example, I can stop making it bigger. Let's just say we had something like sodium acetate. Now, sodium acetate here is a salt that when it's in solution, it's a strong electrolyte, will break apart into a sodium ion and an acetate ion. So when we look at really the components of the salt, what we really want to think about is sort of where these guys come from and will they continue, for example, to react with water. So clearly sodium falls under what we just talked about up here. That most likely came from sodium hydroxide. It's probably the base of where we got that from. Acetate most likely came from what acid? Acetate most likely came from acetic acid. Yeah, so it most likely came from acetic acid here, which is a weak acid. And that's probably the acid and base that basically came together to produce this salt of sodium acetate. So because our acetate part here came from a weak acid, this is going to be its conjugate base, right, essentially. And as we can see here, this conjugate base is going to be relatively strong. And when we talk about sort of a salt and it being relatively strong, what we're talking about is really the ability to continue to react with water. It's not strong like a strong acid or a strong base, but it has that ability to kind of continue to react with water and go through a hydrolysis reaction. And that's essentially what's going to happen here. So when we have the salt floating around in the solution, it's an aqueous solution. There's water in there as well. You're going to have actually just the acetate part going to continue to react with water in a hydrolysis reaction. Now, it's also really important, as I mentioned, to think about where these things came from. So we know that it came from a weak acid. We know that in this case, this would be its conjugate base. And the importance of that is you now know essentially how it should react with water. It should react with water as a base. And the Bronsted-Lowry definition of a base is something that will accept an H plus. And that's what's going to happen. The water is actually going to send the H plus over to the acetate, and it's actually going to accept it. The result of that is we will make acetic acid, which, by the way, this always happens. You always make where it came from. So you always make where the salt basically came from in this reaction. And we would then produce some hydroxide here as the water gave away its H plus in this particular case. Questions on that? And that would be the hydrolysis reaction here. When we write this equation correctly, we can see a couple of really important things when we look at it. I see on the product side hydroxide, which means we should expect this reaction or this solution to be acidic, basic, or neutral. This should be basic because we are producing hydroxide. So before you ever do the calculation by writing this equation correctly, which you need to be able to do, you already know that this thing should be basic. I will tell you that in this particular problem, if you're given this problem, you're asked to calculate the pH of the salt solution. You most likely will be given the Ka value for acetic acid. Do I need to use a Ka value in my calculation here? I should be using a Kb value. So again, this is the importance of being able to kind of write these equations correctly. It helps you with the calculation part. At this point, we could go through the calculation, which is basically an ice table. And you would use the initial molarity of your acetate. These guys would be zeros. We would do our X's like normal. We obviously would solve for X here. And again, as we solve for X, though, it is going to be the hydroxide concentration. So that's going to equal the hydroxide concentration, which means a little POH action first and then into the pH here. So this is what is considered a basic salt. And if you have a salt that basically comes from a weak acid, its conjugate base will continue to react with water. The result of that will always be that it will basically take an H plus from the water, and that will always result in hydroxide being formed. And these salts should always be basic. And again, you need a Kb here. Obviously, that's where you would use the Kw equals the Ka times the Kb to flip it around, because again, you probably will be given the wrong sort of K value. Any questions on that there? It's essentially what I just wrote there. Now, there's also salts that are acidic salts. So, for example, if we take something like ammonium chloride most likely came from a couple of things. What base did ammonium chloride probably come from? Right, which is a weak base, right? And probably the acid in this case was hydrochloric acid, right? So these two guys, when they react, are going to give you a little ammonium chloride in this case. So in this particular case, we want to look at both of these things and determine if any or both of them, by the way, they could possibly be both go through hydrolysis. Are they going to go through hydrolysis? So clearly we should hopefully be able to eliminate the chloride as it comes from really a strong acid. So that's not going to go through hydrolysis here. But our weak base here, this guy comes from the weak base, which means it will also go through hydrolysis. Because it comes from a weak base, it's going to basically be its conjugate acid. And that means that when the NH4 plus reacts with water in this case, it is going to act as an acid, which means it's actually an NH4 plus in this case that is going to send the H plus over to the water. The result of that, there is a little H3O plus being formed. And once again, you will always make where it comes from, which is the NH3 in this particular case. This is also why if you have trouble writing the equations, you want to make sure you look at the question, because it will give you that information because you probably will have in the question the KB value for NH3. So that should tell you, oh, that's probably what's on the product side. So you oftentimes will have a lot of that information in the problem. You just got to make sure that you look for it and recognize it if you're not sure. This is going to, obviously, in this case, without doing any calculation, we should expect this to be acidic because we're producing H3O plus. We also would definitely need a Ka value here when we would do this calculation. And this calculation is just like the other one. It's going to be a nice table with the initial concentration zeros, minus x's, plus x's, and initial minus x, x, and x. Once again, here, when we solve for x, in this particular case, it actually does equal the H plus concentration, which means we can go directly into the pH at this point. Any questions on that? So if you have any type of salt that basically was derived from a weak base, it will always go through this type of hydrolysis where the salt will react with water and basically donate a H plus over to water and produce H3O plus. We should always produce an acidic solution at this point, which obviously you need a ice table to do so. Any questions on that? Now, in addition to this type of salt, there's also some other salts that can basically form an acidic solution. And those are salts that basically have metals. So metals with small positively charged charges like chromium, beryllium, a lot of transition metals, aluminum, for example, can actually also act as a acidic salt. And so just to kind of demonstrate what this is basically an aluminum ion floating around in solution. It's really surrounded by waters. So you basically have an aluminum, and directly attached to that aluminum, you have 6 waters. I'm not going to draw all the waters out. I'll just write them as water here. That's 5, I think. 3, 4, 5. Now, the 5th one, or 6th one here, I will draw out, and it will look like this. Obviously, it's the oxygen side of water, which is more negative, would be attracted to the positive aluminum because it's electron deficient. And what happens in this situation is, and by the way, it has an overall +3 charge because aluminum is +3 and water is neutral, right? So even though there's 6 waters, aluminum is still +3. Another water will just roll through, and essentially what will happen is it will grab off one of those hydrogens from the water that's attached to the aluminum. The result of that is it will then produce H3O plus. And if you look at this scary thing here, which you'll know how to name in a later chapter, if you look at it, we have 5 waters still intact, 1, 2, 3, 4, and 5. When we lose the 1 hydrogen, we're left with OH, yes, which is right there. And that's OH minus, which is why +3 now becomes +2. And that's where everything sort of ends up at. And we get this sort of complex ion happening here, and we get the formation here of basically H3O plus, which will make it an acidic solution. So a lot of transition metals have the ability to do that. Aluminum definitely has the ability to kind of do that. Sometimes they'll hook up with 6 waters, 4 waters, depends on sort of the charge. Typically things with larger positive charges will end up with like 6 things attached to it, or 4 things. Things with smaller positive charges will have 2 or 4 things attached. Those waters are what are referred to as being ligands. And they're able to basically donate a pair of electrons basically to the aluminum, which is electron deficient because it has a positive charge, right? That's how you become positively charged. You lose electrons. So you have less electrons than you started with. So it's able to accept some of those electrons. Any questions on that there? All right, let's try some here. Take a moment here and calculate the pH here of this solution, 0.45 molar potassium chloride. Okay, let's take a look. So first off, if you're not sure where you should start, you should really start with the salt. And again, pretty much salts are strong electrolytes, which means when they are in solution, they are going to pretty much 100% break apart into their ions. And that's really what you want to kind of think about is, you basically will have two ions in any salt. You want to think, will any of these continue to react with water and continue on? So if we look at first off here, our potassium, that is definitely group one, which means that that's going to be considered a neutral salt because in most cases it probably came from something like potassium hydroxide, which is a strong base. So we do not need to worry about that. The chloride there is also most likely came from the acid HCl, which is a strong acid, which means, frankly, we don't have to worry about that guy continuing to react with water. So this is basically going to be a neutral salt, and we should expect really the pH here to be 7 in this case, as that's pretty much where that salt comes from, KCl and some water, the reaction basically of these two things here. So again, sometimes it's good to think about a step back as to sort of where it came from, so that you basically can figure out whether or not it will go through hydrolysis here. We would not expect a hydrolysis reaction basically to happen here. They're just going to kind of float around and hang out, and nothing much is going to happen with them. Any questions on that there? All right, so let's try one where there is a calculation. So perhaps there is a calculation on this one. Consider a 0.3 molar solution of sodium fluoride. The Ka value for hydrofluoric acid is 7.2 times 10 to the minus 4. All right, so take a few moments there, see what you come up with on this one. Okay, let's take a look at this one. So we have obviously here a little sodium fluoride. And we want to think about, again, sodium fluoride here will break apart in solution to a sodium ion and a fluoride ion here. So we want to again determine if anything here is going to go through hydrolysis. So as we talked about a number of times up to this point here, we have our sodium, which is really group one, pretty much a neutral salt, so we don't have to worry about it. Our fluoride most likely came from, it does sort of give you that information right there, which is HF. And we also have a Ka value for the HF, which tells us that's a weak acid, which means that this right here would be the conjugate base. And frankly, it's going to then go through hydrolysis because that's where it comes from. So we will get a hydrolysis reaction that's going to occur with the fluoride ion. It will react with water and it's going to react as a conjugate base. And logic also tells you, hopefully, that it does not have an H to give, so it can only receive, in this case, the H plus. And that's going to give us HF, which once again is where it comes from. And that's what I was saying earlier. If you weren't sure what you might get there, that's pretty much what you get there. And that's usually given to you a lot of times in the problem. So you kind of have the other half of the equation a lot of times given to you. We will also produce hydroxide in this particular case, as the water is going to give away its H plus. So without finishing our calculation or doing the calculations, we should already know that this solution should be basic, right? And we also should know that what type of K value should we be using? KB, right? But we're not given a KB, we are given a Ka, which is very common in these type of problems. They kind of give you the other K value that you need. So these are things that you want to kind of think about as you write the equation and you're doing it. Now we could just get into our ice table here. That's going to be 0.3. That's going to be 0 and 0. Change here will be minus X plus X plus X. When we get to equilibrium here, 0.3 minus X, X, and X. Any questions on that so far? This is going to go into our K expression, which would be our products divided by our reactants. And as you just correctly told me, this is a KB value. So we probably need to calculate the KB value here. So this is where we can use KW equals KA times the KB. That means that the Kb value will be our 1 times 10 to the minus 14, which is our Kw, divided by our Ka value of 7.2 times 10 to the minus 4. That is going to get us here. Punch it in there with the right numbers. That might help. All right. So it's going to give me a 1.4 times 10 to the minus 11. So again, why it's really important to write this equation correctly, so we know that we are using the right K value. So that would give us 1.4 times 10 to the minus 11 equals x squared divided by 0.3 minus x. I'm going to assume that x is equal to 0 here. That will then give me x squared divided by 0.3 equals 1.4 times 10 to the minus 11. I'm going to multiply to the other side and also take the square root. So again, times our KB by 0.3, then take the square root of it. And that's going to give me an x value here of, we'll call it 2.04 times 10. A lot of zeros, 1, 2, 3, 4, 5, minus 6, I think. We did make our assumption, so like normal, we want to check it, so we're going to divide it by 0.3 and times it by 100, and we're nowhere even near 0.1%. So the check here is good. You should, again, make sure that you do check it. Because of that there, we can see that the X value in our table is equal to the hydroxide concentration. So remember that we could get the POH here directly. You can't get the pH. So the POH here is going to be negative log of, we'll go with 2.04 times 10 to the minus 6. Going to give us a 5.69. Again, also why it's important to understand what's going on and writing your equations. If by some chance you got confused and you thought this was the pH at 5.69, that's acidic, and this definitely should be basic. So again, that should not make sense to you. And these are, again, things you just want to think about. To finish up here, we'll take our 14 minus that, our 5.69, and that will get us our pH of 8.31. Which is basic and does make sense in this particular case. Any questions on any part of that calculation there? Okay, let's then try another one here and make sure. Maybe it will turn page. Maybe we'll try another one. All right, so let's try this one here. Calculate the pH of a 0.75 sodium. Okay, so let's take a look. We got sodium cyanide here. So once again, in solution, we're going to get this guy to break apart. And we should have a sodium ion and a cyanide here. We've already discussed sodium, which is group 1, which means it's neutral. Our CN minus probably comes from this acid, which we know is a weak acid, as they gave us that. And again, because this is a weak acid, this would be its conjugate base, and it would be relatively strong, and will go through hydrolysis. So that is the part of the salt here that will go through the hydrolysis. And once again here, it's going to act as a base, which means it's going to accept the H plus. And once again, it doesn't have an H to give either, so it can't do that. That will make, once again, always where it comes from, which is also given to us here in the problem. And again, here we will produce hydroxide. So just like the previous example there, we should also expect this solution to be basic, just really based off of the reaction that is occurring. Any questions on the equation there? All right, so we're going to go with molarity here, 0.75, 0 and 0, minus x plus x plus x. 0.75 minus x, x, and x. Any questions on the ice table here? This will go into our K expression, which once again will be our products divided by our reactants. Obviously, we're leaving water out like normal. This is a K, A, B, C, D, F, G. This should be a K. Could be a KB. Again, we know that because of our equation. So we should be, again, using our KB value. So like normal in these type of problems, you will have to switch it. So our KB here will be 1 times 10 to the minus 14 divided by our Ka value of 6.2 times 10 to the minus 10, I think. And that's going to get us 1.6 times 10 to the minus 5. And we'll pop that in there. 1.6 times 10 to the minus 5 equals x squared divided by 0.75 minus x. The assumption worked good last time, so why not try again? And oftentimes it will work pretty good with these. We're going to assume x is equal to 0. That's going to give us 1.6 times 10 to the minus 5 equals x squared divided by 0.75. Once again, I'm going to multiply and then square root it. Yeah, it's coming across. So taking our 1.6 to the minus 5 times it by 0.75 and then square rooting will give us an x value here. I'll go up on top so it's easier to see. 3.46 times 10 to the minus 3. We do need to check it, so we'll take that divided by 0.75 times it by 100, and we're still good. We're like at 0.4%. So the check here is good. About 0.4%, I think. That means that this x value will equal from our table, much like the last time, the hydroxide concentration. So we could then go into our POH. Giving us a POH here of 2.46. And now we can subtract 14 there and get to our pH. Minus 14 looks like 1154 in this case, which is definitely basic and again what we would expect based off of the original equation that we wrote. Put on any part of that there. So these calculations not too difficult, really just still a nice table. The key is to recognize what you're dealing with. Is it an acid? Is it a base? The correct Ka value or Kb value? That's where a lot of people screw up on it. They use Ka instead of Kb and vice versa. Yeah. What's that? Right here? I just went a little higher because it looked a little low. So yeah. Other questions? All right, so these are salts. We did a couple here that produced hydroxide. You obviously could have an acidic salt like we talked about that would produce H3O plus. The only real difference is once you get X in those, you just go right into the pH because that is the H plus concentration, but pretty much works the same way. You most likely will have to convert the Kb value to a Ka value that's given to you, and everything works the same. Any question on salts here? So here's a prettier picture of the aluminum that I drew. But again, you can see basically this is the aluminum in the middle. We have our oxygens there. And again, it's just going to grab off one of those and make our H3O plus. Now, up until this point, we really looked at salts where only one part of the salt went through hydrolysis. And it is possible that both parts of the salt could go through hydrolysis. For example, if you had something like ammonium nitrite, that is NH4 plus and NO2 minus. That comes from a reaction, say, of nitrous acid and ammonia. That is a weak acid. That is a weak base, which means both parts of the salt has the ability to go through a hydrolysis reaction. The calculation with both of them going through hydrolysis is quite complicated. So typically what we do in this situation is we actually compare the Ka value to the Kb value. And if the Kb value for the anion is greater than the Ka value, then you will basically do the basic calculation and you would do the Kb calculation and ignore the other guy. If the Kb value for an anion is less than the Ka value, or the Ka value is larger, you would assume that this solution would be acidic, and you basically would just do the Ka calculation. And if they're about the same, then you're looking at a neutral situation happening in that particular case. So if you have a salt where, again, both parts can go through hydrolysis, you would compare the Ka to the Kb value. And basically, whichever one's larger, the Ka or the Kb value, then that is the calculation that you would do. And you would assume either it's going to be acidic or basic, depending on which one is larger. And that's sort of what this little table kind of goes through here. These are our guys going to be 7. Something comes from strong acid, strong base. Basic, if we have something that comes from a weak acid. Acidic, if it comes from a weak base. And again, here we have guys that both can go through hydrolysis. So these guys will depend on the Ka versus Kb value. And then obviously some of our metals that have a larger +2, +3 charge will also go the acidic way. Any questions on any of that there? So let's talk then a little bit about oxides. Oxides are obviously elements that have oxygen involved, and typically these oxides will, when they react with water, for example, become either acids or bases. So a lot of these guys over here in group 1 and group 2, these are our basic oxides. And that means that typically when they react with water, they'll form bases like sodium hydroxide, potassium hydroxide, barium hydroxide. Over here in kind of the bluish area in our non-metal situation, these are our acidic oxides. And when these guys react with water, they'll form acids. So for example, if you took water plus a little carbon dioxide, will form a little carbonic acid. So this guy here will form nitric acid and so forth. So a lot of these guys reacting with water is where we'll get a lot of our acids formed from, especially our non-metal action. And then we have some that are amphoteric, and much like what we talked about, amphoteric are guys that really could go either way. They could either form an acid or a base when they react with water. But again, sort of to the left where we kind of find our bases, basic oxides, upper right, kind of the non-metal region is where we find our acid oxide. Now, up at this point, we talked about a couple of definitions of acid and bases. We have the Arrhenius definition, which is something that produces H+. We have the Bronsted-Lowry definition, which is a proton donor. So, of course, we want our good friend Lewis that has a definition of an acid and base. And when we think about Lewis, right, we think about Lewis structures. And when we think about Lewis structures, that involves what things? You draw Lewis structures with dots which represent electrons, yeah. So not surprisingly, Lewis acid and bases definitions involve actually electrons. And a Lewis acid is a substance that will accept a pair of electrons. And a Lewis base is a substance that will actually donate a pair of electrons. So you have to have electrons to be donated. They have to be kind of available electrons. So a lot of things that are polar and have non-bonding electrons are good Lewis bases. Things that are negatively charged ions, the only way they become negatively charged ions is they gain some extra electrons, so they have some to give. So those are also good Lewis bases. So for example, here our hydroxide going to donate a pair of electrons over to our H+, and anything that is positively charged, right, is electron deficient, which means it wants to accept electrons, and that would make our guy here our acid and this our base. And over here we have ammonia, which is a polar molecule, has these non-bonding electrons, going to send them over there to our hydrogen. It's going to accept it, which makes it the acid. It's going to donate it, which makes this the base. So good Lewis bases, as I mentioned before, things like water, things like ammonia, things like chloride, hydroxide, these type of things are good Lewis bases. They're polar molecules. Things that are Lewis acids are typically a lot of times things with positive charges. And again, they're sort of electron deficient and they're able to sort of accept those electrons as well. By the way, we could still apply our Bronsted-Lowry definition in this case. If we applied the Bronsted-Lowry definition, what would be happening is this H plus is being donated over to the OH minus, which means H plus is still the acid and the OH minus is still the base. Here, same thing, donating over here to ammonia, which would mean, again, the H plus is the acid and the ammonia is the base. So you actually get the same overall definition of acid and base when you use Lewis or Bronsted-Lowry, but one again talks about protons being donated, Lewis electrons being donated. The benefit of sort of the Lewis acid base definition is you could apply it to something like this, where here we would have our pair of electrons going over to boron. Boron is an exception to the octet rule. As you might remember, it can make an incomplete octet because it's essentially electron deficient. So it's happy with 6, so it's got room for some more. So it's going to actually accept it here. And in this particular case, we could apply in this case, this would be our Lewis acid, this would be our base, and we could apply it with no hydrogen being transferred. It is also, we will definitely see Lewis acids and bases again when we talk about complex ions in a later chapter. And that's essentially how complex ions are thought of, as a Lewis acid base situation. Frankly, the salt that we saw earlier, where we had the aluminum with all the waters attached to it, that's aluminum, which is positively charged. That is oxygen, which is a polar guy that has the electrons to be shared. That's a Lewis acid base situation that's really happening with that aluminum with all those 6 waters basically attached. That's essentially what is going on there. So we definitely will see Lewis bases. It pops up a lot in some other chapters as well when we talk about complex ions and stuff like that. It's sort of a nice generic sort of definition as well that you could apply involving electrons and don't need an actual proton being transferred. Any questions on that? All right, so let's talk a little bit about polyprotic acids. I will talk a little bit about. So polyprotic acids are acids that obviously have more than one hydrogen to give. We sometimes use generic formulas to represent a couple different types of acids. HA is sometimes referred to as a monoprotic acid, which means it has one hydrogen give, and when it does, it will give away an H plus and an A minus. So that's something like HCl, for example. We could have a diprotic acid, which has a couple of hydrogens to give away. And overall, what will happen is it will give away 2 hydrogens overall. And this guy will have a -2 charge. And we could have a triprotic acid, which has 3 hydrogens to give. And here overall, what's going to happen is this guy's going to lose 3 hydrogens overall. And the negative guy actually will have a -3 charge here. Particular case. So hydrogens come off acids, especially in polyprotic acids, diprotic and triprotic acids. They come off basically one at a time. So they don't all just drop off. And each time it comes off, you could have a Ka value associated with the hydrogen coming off. So if we take a look at our phosphoric acid, for example, here, the first thing that will happen is our phosphoric acid will lose 1 hydrogen and make H2PO4 minus. And there is a Ka1 value associated with that from the table, which we see right here and right about there. And the next thing that will happen is this guy that's already lost one hydrogen will then lose a second hydrogen and make HPO4 2 minus. And that also is an equilibrium and a Ka2 value, which we see right about there. And this is 7.5 times 10 to the minus 3. That is 6.2 times 10 to the minus 8. And lastly, what will happen here is our HPO4 2 minus will lose its last hydrogen here and become phosphate. And we'll have our Ka3 reaction here. And that's right there. That's 4.8 to the minus 13, looks like. So it is a stepwise dissociation when we have a polyprotic acid that happens. A lot of times we look at like the overall reaction here. And again, we could get that by adding all these together. We add up all these steps together. This guy and this guy cancels, this guy and this guy cancels, and we're left with the overall reaction that you oftentimes will probably look at, which is this guy, and he gives away basically 3 hydrogens, 1, 2, and 3, and phosphate. But again, it does happen in this sort of stepwise fashion, as you can see here. Now, is it easier to remove the first hydrogen or the second hydrogen? It is much easier to remove the first hydrogen in this case. And we see that by the value of the Ka value. So to remove the first hydrogen, for example, here in phosphoric acid is 7.5 times 10 to the minus 3. That is going to be much larger than the K value that we see when we try to remove the second hydrogen. It is times 10 to the minus 8. Because that's a much smaller K value, it's going to pretty much stay together, which means not a lot of the H plus is going to come off in that second hydrogen. Gets even worse when we try to rip off the third hydrogen there, because now we have a minus 2 charge, which means it's going to kind of stay together and not much hydrogen is going to come off. So with polyprotic acids, it's much easier to remove than say the second hydrogen or the third hydrogen. If there is 3, it gets more and more difficult. Again, that's because you're trying to remove something that's positively charged like H plus, and now you have something that has a negative charge, like a -1 charge and a -2 charge in the second case, and that's going to hold it a lot tighter and make it a lot harder for it to basically get removed in that particular case. So ultimately, in a polyprotic acid type situation, it does take harder and harder to sort of get rid of the extra hydrogens. So, yeah, we'll go for it. Why not? Let's take a look at a calculation here, and we'll come back to this here. So let's say we wanted to figure out the pH and pretty much the concentration of everybody going on here. If we started with a 5 molar solution of phosphoric acid, here's our 3 K values. Again, this is basically for our first hydrogen that comes off, right? This is our second hydrogen that comes off, and that's going to be our third hydrogen that comes off. So let's take a look at this calculation here together and talk about how we would approach a polyprotic acid calculation. So clearly, since we want to calculate the concentration of everybody, we might as well start with the first hydrogen that's going to come off. And that first hydrogen that's going to come off is going to have that Ka value that we see there. So what I'll do is maybe here, or not. Oh, there you go. So the very first thing that's going to happen is we're going to have our phosphoric acid. It is going to lose that 1 hydrogen as we talked about, and we'll make H2PO4 minus. That's going to be our Ka1 value, that is 7.5 times 10 to the minus 3. So initially here we are starting with 5 molar in the problem. So we're just going to do a normalized table here. These are going to be zeros. minus x plus x plus x, which means we will have 5 minus x, x, and x. Now, this is going to go into our Ka1 expression, which will be our H plus times our H2PO4 minus divided by our H3PO4. And putting those values in will give us x squared. 5 minus x is equal to our Ka1 value as 7.5 times 10 to the minus 3. I'm going to assume that x is equal to 0 and hope for the best. And that's going to give me x squared over 5 equals 7.5 times 10 to the minus 3. I'm going to multiply the 5 to the other side and then take the square root of it. So we'll times it by 5 and take a square root. And we will end up with a 0.194 as our x value when we do that. We do want to check it, so I'm going to divide it by 5 and times it by 100 here. Divide it by 5, times it by 100, gives me 3.9%, and that is good, which is probably why I changed the number years ago to make sure that the assumption goes good here. So in this case, since that assumption is good, we actually have a lot of questions answered here off of the first table. We know that in this case, the H plus concentration equals X, which means the concentration at equilibrium of H plus should be 0.194. We also know the concentration of H2PO4 minus equals X, which would be 0.194. We also know that the concentration of phosphoric acid equals 5 minus X, which would be 5 minus 0.194, gives us, we'll call it 4.81 molar. So off of this very first sort of ice table here, we just hit a bunch of answers that we were looking for. We got, if we come back to our original question, this guy, we got this guy, and we have this guy's basically answer. But we still are looking for a few other concentrations that are going to require us to look at the second dissociation and also the third dissociation. It's the only way we can find phosphate is in the third part. So let's go then look at the second dissociation here and see what we could get from that. So the second dissociation would be this guy, which will then lose a hydrogen and make HPO4 2 minus. This is going to be our Ka2, which was 6.2 times 10 to the minus 8. Now, initially, do I have any of the H2PO4 still in the solution? The answer is yes, because it came right here at equilibrium, right? And I also have some H plus in there as well, right, from our first dissociation. So these equilibrium concentrations that we calculated from the first table will now become our initial concentrations for our second table. And in this case, it looks like they are both 0.194. And again, we also have this one from our previous table. We do not have any of that one, obviously. The change here will be minus x, and plus x. That means we will end up here with 0.194 minus x, 0.194 plus x, and x. Any questions on that ice table there? So again, our initial is from our equilibrium before. This will go into our Ka2 expression, which will be our products over our reactants. And that's going to give us 0.194 plus x times x divided by 0.194 minus x equals 6.2 times 10 to the minus 8. I'm going to assume that x is equal to 0 because it worked good on the first one, so why not here? That's going to give me 0.194x divided by 0.194 equals 6.2 times 10 to the minus 8. I think I could do that math. That means X is equal to 6.2 times 10 to the minus 8. We could check it here by dividing by 0.194 and times it by 100%. And I think we should be good. And it's nowhere near even 1%, so the check is good. So in this case, by going to this table, we're able to get the concentration of this guy. So the concentration of HPO42 minus is equal to 6.2 times 10 to the minus 8 molar. How about the concentration of H plus? What would it be when I put the X into that? If I take 0.194 and I add 6.2 times 10 to the minus 8, I get the same thing. Yeah, it's basically the same thing. And the same thing over here. If I put it back into here, I'm going to basically get the same thing. So those concentrations are basically going to be the same if we put the X value back into there. Any questions on that there? So looking at what we're trying to find, we just knocked off another one here from our list. So we just knocked this guy off. The last one that we're looking for is the phosphate. And again, the only place that we can find the phosphate is in the last association. So that's what we'll do. We'll look at the last association here. And the last association will be this last hydrogen that's going to come off. And this would be our Ka3 value, which is 4.8 times 10 to the minus 13. Just like last time, we do have an initial concentration of this guy from our equilibrium line. So that will now become our initial, which is 6.2 to the minus 8. We also still have our hydrogen floating around, and we have none of that. So again, both of those from the previous table. Change going to be minus X plus X plus X. That means at equilibrium, 6.2 times 10 to the minus 8 minus X, 0.194 plus X and X. This is going to go into our Ka3 expression of our products over our reactants. And that's going to give us 0.194 plus X times X divided by 6.2 times 10 to the minus 8 minus X equals 4.8 times 10 to the minus 13. I'm on a roll, so why not continue to assume that X is equal to 0 here? That's going to give me 0.194 times X divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. I'm going to multiply the bottom here, and then I'm going to divide the guy up on top. And that's going to give me 6.2 to the minus 8 divided by 0.194. Can give me a 1.5 to the minus 19. We could check it by dividing by 0.194 and times it by 100, and we're nowhere even near 1%. So the check is good here. That means that if we go to our table, that's going to be our phosphate concentration. So our concentration of phosphate will equal X, which in this case is 1.5 times 10 to the minus 19 molar. Question on that one there. Now, if I put that X value back into here, does the number change? If I take 0.194 plus 1.5 times 10 to the minus 19, it basically stays the same. And if you put that X value back into here, it basically stays the same. Any questions on that there? Yeah. What? So it's going to, we're going to assume that it's going to come off. Not a lot's going to come off, but we're going to assume that's going to continue to come off in that case. Yeah. So, because it's basically an acid, and ideally it's going to break apart in solution. But as we see here from the calculation, not a lot of it's going to continue to break apart, right? In this particular case. So if we look at this, right, and the last thing that we were looking to solve for was the pH. And since the pH is equal to minus the log of the H plus concentration, when we look at this triprotic acid actually here, The majority of the H plus came off in which step? The very first step, right? After that, we only got off like 6.2 times 10 to the minus 8 came off, which is a very small amount. Pretty much nothing came off. And then after that, we got 1.5 times 10 to the minus 19 of the H plus basically came off. So if you're asked to calculate the pH, for example, like we were here, and you were only asked to calculate the pH of a polyprotic acid, in most cases, it is safe just to do it based off of the first ice table. You wouldn't necessarily have to do the second ice table or the third ice table, as a majority of the H plus is going to come off in that first hydrogen coming off, which in this case was 0.194, I think. So that means our pH in this case of this acid would be minus the log of 0.194. And that's going to give us a pH here of 0.71, which is definitely acidic. So when you're doing these polyprotic acids, like I said, if you're really only asked to calculate the pH, you really just need to do the first ice table in pretty much all cases, and you'll be able to get probably the right pH. But if you have to calculate the concentration of everybody like we did here, we had to go all the way to the third one, because that's the only place where we're going to find phosphate. So we had to go through all the steps. Then you would have to go through each of the steps like we did here. Any questions on polyprotic acids? All right, we'll wrap it up there.